Hello, this is Britt Caswell with another example video. In today's video, I'm covering example 2 from section 8-1 in the SavvasRealize Algebra 1 textbook. The goal of today's video is to understand the graph of f of x equals ax squared. So, notice this isn't quite the parent function of a quadratic. This is dealing with what's called a leading coefficient, a. So where that a is coming from is it's actually going to be in several forms of our equation. But where you have seen it so far in Algebra 1 is from this equation here. F of x equals ax squared plus bx plus c. This is called the standard form of a quadratic. And so the a we're talking about here is this same a here. Although throughout all of our quadratic forms, that a is definitely the same thing. Okay? And so what I'm actually going to do to show you how this value affects it is I want to show you where this kind of graph is coming from. So I'm going to pop over here to Desmos and let's take a look at that. Come on, Desmos. So right now, here's our parent function. Okay? Our parent function occurs when a equals 1. Okay? I'm actually going to keep that parent function on the screen just so that you can compare it. Okay, so this red one is now going to move and the blue one's going to stay where it was, completely overlapped, okay? So check it out. Watch when a equals 2. Actually, I'm slowly moving it up because it's a slider, which is kind of nice. So here's where a equals 2. Okay, let's enter 3 and see what happens. Let's enter 4 and see what happens. So do you see how for every value of a, my graph is getting narrower and narrower? That's because our a value, what it does is it determines how far up or down the graph moves when I go 1 unit to the side of my vertex. So these have a shared vertex at 0, 0 because nothing's being added or subtracted from the function. And you can see, so for the blue one where a is 1, when I go to the side by 1, I go up by 1. But our red one, right now a is 4, so when I go to the side by 1, I go up by 4. And so that's what causes that narrowing as our a value gets bigger. So now you might be wondering, well, what if I want to make it wider? What kind of values do that? So I'm going to reset to 1. So did you see everything here was narrower? So now we're going to go backwards a little bit. We're going to go towards the wider section. See, so as I'm using the little slider, do you see how the red one is getting wider and wider and wider and wider? And then what happened? It went away. Do you see how it stopped being a parabola? That's because when a is 0, you no longer have an x squared term. And that squared term is what makes your parabola. Alright, so the things that made it wider were my numbers that were between 0 and 1. Alright, so we freaked out at 0 because it turned into a flat line. That's okay. What happens if I push it further? What happens if I go further? Do you see how the graph is upside down? So now, between the 0 and the negative 1, it's still a wider parabola. At negative 1, it's the same parabola as the parent function, just upside down. And then more and more left, the thinner it gets. Alright, so hopefully that's kind of an observation that will help you there. Okay, so let's get you some language for this. So when I'm going to say the absolute value for a, so when just the number for a is bigger than 1, you're getting what's called a vertical stretch. Alright, that's what causes that narrowing there. Savvas is not big on calling it a stretch, they really like to call it narrow. Alright, now the black one, that one's our compression, right? So between 0 and 1, that's where you get a vertical compression. Or Savvas likes to call it a widening. And then down here, when you have a negative number for A, you're going to get a vertical reflection. And then for reference later on, for those of you guys who use these notes, the red one is your parent function. Okay. So part B here, it says, how does the sine of A affect the graph of f of x equals ax squared? And so I touched on it here where when it was negative, it was a vertical reflection, and our positive values had it open up. So the way that I remember that idea is I think about a cheerleader and a grumpy old man. So a cheerleader is positive, right? See her? She's like, yay! Do you see the parabola formed by her arms? So that positive attitude, or that positive A value, is what causes the parabola to open up. But this old man, he's grumpy. Look at him. And sure enough, if I knew how to draw, the parabola formed by his arms opens downwards. So A is like the cheerleader and the old man. So, just get my text box ready. So when A is positive, the graph opens upwards. When A is negative, the graph opens downwards, like our old man. So now it's asking, how does the sine of A affect the domain and the range? Okay. So let's start with our domain. Take a look at the graph. Remember, the domain is all the x values that the graph passes by. So all of our positive a's go for forever to the left and forever to the right. Well, so do all of our negative a's. See that? That goes forever to the left and forever to the right. So there is no effect on the domain when we have a negative a. All right? Let's talk about the range, though. The range is our y values. So when a is positive, we're on the positive y-axis. Okay, so I'm going to put that on there. When a is positive, our range is y is greater than or equal to 0. Okay, that's how we write it as an inequality. But when a is negative, what's happening? Do you see how our graph flips upside down? So instead of going for y is greater than 0, this turns into y is less than or equal to 0. So that negative a value flipped the sign on our inequality. So there we have it, guys. That is understanding the graph of ax squared. So that's so you know what a does. Soon we're going to learn about other transformations. So until next time.